All right, so now we're going to move on to 9.4, assignment 9.4. Should have already done these problems. If you haven't, pause it, do the problem so you know what you can't do. I'm going to do these 3 problems. Reminder, you can't do the last 2 problems on this worksheet, so please don't try them. You'll be able to do them by the end of today, but not yet. You're going to have to do them as part of once we talk about the force between 2 electrical charges, or Coulomb's law. We have here a positive rod is brought near a neutral electroscope. The electroscope is charged by induction. Induction means they're not touching, right? So we're going to go ahead and do this. We're going to say, all right, I've got my positive rod. So my electron's going to flee the tops and at the bottom, but I haven't actually charged it, so the positive is still sitting on the top. So this is, in fact, B. 4, electroscope is charged by induction by a conduction by a positive rod. So if I touch it, what happens here is the positives, so the electrons jump off because I'm charging by induction. That means I have less electrons, so the top and bottom, the electrons spread around and all the positives are revealed everywhere. And so again, that would be, oh, I'm lying. First answer wasn't B. The first answer was A. This was A, right? Because that's positive, negative, bottom. This is B. There we go. We're getting better. Okay, negatively charged rod brought near a neutral electroscope. Again, we're not touching. We're going to assume there's no charges jumping across. So this is negative approaching. Negative. Tops plus minus. And then minus plus. We know the minuses flow downwards to get away from this evil. And so therefore, you end up with positives on top, negatives on the bottom, or back to A. And basically, if you look carefully at the words for the 2, they're virtually the same. Okay? All right, so that's how you do these problems, and hopefully going forward you do that. Now, there's a question that comes up from time to time. They're like, wait a second. I thought what happened was the rod, when it's positive, this is 4 we're talking about, when it touches it, the positives jump off. Now, what's interesting about this interpretation is it gives you the right answer. Remember, for 100 years, we didn't know which one did which. And if you don't know which one did which, then it's going to give you the right answer every time. And so part of what we can do here is we can pretend like positives move. They don't, but we're going to prove because they give us the same answer, and life's better. So if you thought a positive rod touched an electroscope and you thought the electrons didn't jump on the positive rod, instead the positives flew onto your electroscope, well, you and Ben Franklin would agree on exactly what happened there. And actually most of the great physicists for 100 years that talked about electricity would all agree with you, including people that generated things like generators and the lights you have over your head. All of them would agree that that is a correct interpretation. It's not true. But, so I'm telling you the truth when I say electrons move the other way, but you can actually interpret things that way. All right, so we're going to pause. We're going to stop working on 3.5. If you have additional questions, you need to send them to me directly, and I will make additional video posts and that sort of thing. But for right now, what I'm going to do is I'm going to go back to 9.1, and we're going to spend some time talking about Coulomb's law. Who's this guy Coulomb, and why does he get to make a law? So as we go back in time, we're going to, where's my new file? New, there it is, file, new, boop, new. Don't save, and so here we go. So looking at this, I have Coulombs Experiment. Now Coulomb was the first guy to say, look, if there's a force involved, I want to know what the force is. And so he would take 2 charged particles on the ends of strings, essentially on pith balls, bring them close to each other. If they're the same charge, he'd watch them repel each other. And by using a bit of sorts of experiment, he started to come to the conclusion that he could tell like forces repelled, opposite forces subtracted from each other, and he realized that both charges matter. Like if this was a super big charge and this was a small charge, it was less powerful than if both were super big charges. So because of that, he came up with Coulomb's law. Coulomb's law is the force of electricity is equal to the one charge and the other charge. Now, I use Q's for charges because we're already running out of letters. You would think C would be a logical choice, but his name starts with a C, and so that made that impossible to make the charged letter for reasons we'll get to in just a moment. He then noticed that the forces were twice as strong 4 times as strong when he got twice as close. 9 times as strong, we got 3 times as close. So he realized that there was an r squared on the bottom. He also realized that he was making up what charges were, so he couldn't possibly make it so there was no constant, so he made a cute little k out in front. And then he read about an experiment involving a glass jar, a string, a stick, and 2 charges now instead of a masses, and another charged ball that he could wiggle on the outside. And the amount this twisted would determine how much force is being applied. So again, he could derive K from this. Okay? So Coulombs experiment is very much an old school experiment, except he's doing with charges. He created Coulomb's law. This is Coulomb's law. Force of electricity is K. This right here, K, is a universal constant. We'll get to in a second what its value is. There's a constant. Q's are charges, and they're the 2 charges involved. Those are charges. And then the distance between them. This is the distance between them. Center of charge to center of charge. And this is our friend force. Now, force is going to be measured in newtons. A distance between is going to be measured in meters. So what do we measure charges in? Well, obviously, the guy named Coulomb's the one that invented this, so therefore charges being measured in coulombs, meaning that we can't use a C for this. We can't use the same letter for both of those. That would be way too confusing. And so therefore, we're going to use Q for charge, and we're going to measure it in C's, which is coulombs. The universal constant, which he measured, is actually a fairly large constant. It's 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. All right. Now, this should look familiar. What? This should look familiar. This is the exact same format of force of gravity. And so these are the 2 forces involved with the 2 major forces we see in the universe. There's actually 2 more what we call primordial forces, or forces that are not just general. We don't simplify in some way. All those forces have the following format. They have a constant of some sort in front. They have distance squared on the bottom. One of them has 2 variables here. They're actually z's, so I should go ahead and make them z's. The other one is a little disturbing because it actually uses a letter L, and there's only one of them. So those are the 4 forces: strong force, weak force, force of gravity, and force of electricity. All have roughly the same format. That led a guy named Albert Einstein, who usually was right, to conclude that all these forces are the same forces. We're just dumb humans who can't see them clearly. It's been 85 years. That theory is starting to head towards the land of the lost. But it is interesting that they have the same format, which suggests there has to be similarities between them that would be useful. But right now, nobody's come up with what those things are. And so, and hence, we're left with a question. Is in fact all the forces the same? Again, most experimentation that we've tried, there's things like we know force of electricity can be carried by light particles. Force of gravity would therefore have to be carried by something called gravitons. We don't see gravitons. We've gotten down to the point where we should be able to measure them. We don't see them. Okay, so there's lots of little things like that that suggest these may not be all these forces may not be the same forces. That in fact it might be something simpler that relates to these things. But I'd be a bad physics teacher if I didn't tell you that this was at least an idea that physicists to this day are still working on trying to figure out. But that in mind, we have 2 examples. So try example number 1, example number 2. I will be doing them in just a moment. So pause your feed, and then I will start in 5, 4, 3, 2. All right, so now we get to the land of negative charge. A negative charge of negative 2.00 times 10 to the negative 4th Just for the record, a Coulomb is a really large amount of charge, so you generally speaking don't deal with whole Coulombs. Whole Coulombs cause people to die, so we're not talking about something that you see very often. It's brought next to a positive charge, which is 8.00 times 10 to the negative fourth coulombs. They're separated in space by a distance of 0.300 meters. Question, what is the force between the two charges? We just use force of electricity is equal to KQQ over D squared. Force of electricity would therefore be equal to 9 times 10 to the ninth times the first charge, which is going to be negative 2.00 times 10 to the negative fourth, times 8.00 times 10 to the negative fourth, all over 0.3 squared. And then we're going to put that in our calculator. Again, if you're not using scientific notation, you're on your own because you're making your life harder for no good reason. But enjoy making your life hard if you'd like that. Exponent negative 4 divided by 0.3 squared, and I get 16,000 newtons. 16,000 newtons. Okay? So 16,000 newtons. It's negative. Well, what does negative mean? Well, here's an interesting thing. When one of these things is positive and one of these things is negative, then you're going to get a negative answer. If they're both positive, you get a positive. Both negative, you get a positive as well. So what does it mean? Well, interesting enough, it does mean direction, but it means weird direction. So electricity has a kind of weird thing with directions. Negative is attractive. Yes, high schoolers, it is negative to be attracted to each other at your age. So therefore, negative is attractive, positive is repulsive. It's better to be repulsed by that situation. So when opposite charges are attracted, you're going to get a negative here, so you realize they're attracted to each other. When you get when the net charge is positive, when you get a positive force answer, they're repelled from each other. It's not a left negative or positive direction. All right, going to do problem number 2 now. I don't know if the answer is correct, so I'm going to double check right now. Okay, so I have 2 charged particles. That means force of electricity is equal to 9 times 10 to the ninth, K. Oh, I don't want to do that down. What just happened there? Stop. All right. 9 times 10 to the ninth times not negative, positive in this case, 6.00 times 10 to the negative fourth. It says 2 charges of that, so 6.00 times 10 to the negative fourth. That's often said in these problems. That's there. And then divided by the distance between them, which is 0.5 squared. Put that on my calculator, and I get 1.3. I get 12,960. So we're going to write that as 13,000 newtons. All right. So these are easy enough to do. There's a whole worksheet devoted to that, but I need to talk about one more thing before I send you to that worksheet. And so I do apologize. We're going to stop this video because I didn't quite time this right. We'll get another video started, and then we'll be free to be done with today.